In this video, we're going to continue our discussion about mole calculations. Uh, in the early videos, we already learned that the concept of mole, and as important as mole, we learned that all of the mass numbers on the periodic table, they actually have another meaning of molar mass, meaning in one mole of any of these elements, you're going to have this many grams of the elements. So that turns into making these numbers very useful numbers for us to do calculations, such as we can convert a certain number of mole of elements into the mass of these elements, or the other way around, we can turn the mass of any elements into the mole of the elements. And then in turn, we're going to turn the mole of elements into the number of atoms of the elements using Avogadro number. So we've done the calculations around the mole of the single elements already. So in this video, and we're gonna start learning about how do we deal with compounds. As we know, compounds is composed by multiple different kinds of atoms or elements. So we can adopt the same idea about the mole and the molar mass to molecules or compounds. So here, let's take a look at the example, okay? So when we look at the chemical formula of this compound Al2SO43, you can quickly challenge yourself how to name this guy, okay? Alright, so this guy is an ionic compound. Metal aluminum here is the cation, and the polyatomic ion sulfate is the anion. Okay, then you also want to quick challenge yourself. Do you recognize all of those little subscript numbers? Why they're there? Well, of course, it's because of the charge, right? So, quick review of this compound. Okay, now this aluminum is actually a type 1 metal, which has positive 3 charge. Whereas sulfate is a polyatomic ion with actually negative 2 charge. Now, in order to balance the charge between positive 3 and negative 2, there are a couple of ways of doing this. A lot of people tend to do crossing these two numbers down to make the substitute number here 2 and 3. So in order to show multiplicity of the polyatomic ion, you can't just put number 3 there, you have to actually cover it up with parentheses. So this is aluminum sulfate. Okay. Now, each one of the elements in here actually has its own molar mass. So if we are talking about 1 mole of this compound, you are looking at multiple mole of each element. Okay, there are 3 elements here: aluminum, sulfur, oxygen. If we count, okay, there are 2 aluminums in every 1 aluminum sulfate. That means the ratio is going to be 2 to 1. So in every 1 mole of this compound, there are going to be 2 mole of aluminum. Now similarly, you can count this 3, okay, multiply into everything into the parentheses. So there are technically 3 mole of sulfur and 3/4 mole of oxygens. And then you can add them up. If it's very important, okay, you are doing addition, okay? So for instance, you can calculate the molar mass of aluminum, multiply the factor 2 here, okay? And then for sulfur, there are 3 of them, oxygen 12 of them. So you can find the mass composition of each element in this compound in 1 mole, okay? In 1 mole of compound. So in 1 mole of compound, total mass is going to be 2 mole of aluminum, 3 mole of sulfur, 12 mole of oxygen's mass adds up. So this will be the molar mass of aluminum sulfate. Okay, so this is so you can see the molar mass of the compound can be calculated from molar mass of the single elements by including the factors. Okay, now we do have, since it's particularly referring to, specifically referring to molecules, so we also call the molar mass of molecule. Another way of calling it is molecular weight. Now, since most of the chemistry are dealing with molecules, so you're going to see this molecular weight a lot, okay? Also, I want to address this. So, okay, the unit of molecular weight is gram per mole, or gram/mole. Okay, In other words, if you're given a chemical formula or a name of the compound, you should be able to write out the formula of the compound, and then if you have a periodic table next to you, you should be able to calculate the molecular weight of any compound. Okay, now let's take a look at a few more examples here, just for practice purpose. Oh, excuse me. Now, of course, you're going to need a periodic table to find the molar mass of the single elements first, okay? But let's take a look at a few quick examples of calculating the molecular weight here. Now, feel free to pull out a periodic table anywhere, if online or from other websites, and see if you can try to calculate the molecular weight here by pausing the video. All right, so hopefully you already tried maybe one or two of these, or and I would strongly recommend you try it first before you continue watching this video, okay? Now, this compound, okay, is called, well, you can challenge yourself over here how to name any of these compounds. H2S is actually a kind of acid. For naming compounds, the most important thing is to actually recognize what type of compounds first, and so you can follow different rules. So this is an acid without oxygen, so it's going to be called hydrochloric acid. Now, because of positive 1 charge, negative 2 charge of sulfur, that's why there's a 2 here. Hydrosulfuric acid, I'm sorry. Now, the molecular weight is going to be adding up the hydrogen and the mass of the sulfur. So, hydrogen, the molar mass of hydrogen is 1.01. Now, don't forget that there are factor of 2 here, so that means there are 2 hydrogens. And the sulfur is going to be 32.07. We already talked about this, okay? You take 2 decimals of the molar mass of any element, okay? So these are 2 hydrogens, and this is sulfur, or you can put a 2 in front, okay? 2 hydrogens. Now you're adding them up, okay? I can't overjudge this. Even though they look like H2S, they're not multiplying, okay? You're adding them up. This compound is composed by 2 hydrogens and 1 sulfur. Once you add them up, you get a number. This is the molecular weight. Okay, we're trying to calculate molecular weight according to this formula. The unit is gram per mole. All right, let's look at the last one, CO2. The name of this guy is carbon dioxide. Non-metal combination, no ions. Okay, you have to use those prefixes, mono, di, tri, tetra, penta, blah, blah. Okay, so this is 2 oxygen, carbon dioxide. Carbon is 12.01. This is the molar mass number you can obtain from the periodic table, plus the oxygen, 16.00. Now, because there are 2 down here, that means times 2. Now, we didn't really put the 2 in front of the carbon because there's no number here, that means it's a 1. All right, add them up, make sure you do the multiplication first. You're gonna end up to be 44.01. Again, this is the molecular weight, grams per 1 mole. Okay, every 1 mole of carbon dioxide weighs this many grams. All right, let's take a look at this one, okay. This guy is called magnesium nitrate. There's no need to say dinitrate or 2-nitrate. It's ionic compound. Magnesium is type 1 metal with positive 2 charge. Nitrate is negative 1. That's the reason you need to double negative 1 to balance the charge. Anyway, magnesium nitrate is composed by 1 magnesium. There's no other number around it, so you can look it up on the periodic table. You'll find the mass number, or the molar mass of magnesium is 24.30. Plus nitrogen and oxygen, but both there are more than 1. Nitrogen has, because of the number 2 here, so it has 2 of the nitrogen, 14.01. That's the molar mass of 1 mole of nitrogen. You have a factor of 2 here, so times 2. Plus the oxygen, 16.00. That's the molar mass of the oxygen, but you have 2 by 3. Okay, 6. Again, among different elements, you are always doing addition. Okay. So this is magnesium plus 2 nitrogens plus 6 oxygens. Okay, so total is 148.32. Again, we're always keeping 2 decimals at the end for each molar mass, gram per mole. Now, once you are able to calculating the molecular weight given any formula, then we ought to be able to do all of those conversions we have done with the single elements. Let's quickly summarize what we have learned about the mole calculations before we jump into the actual example, okay? So if you have a mass number, which is in the unit of gram, you should be able to convert this into mole. Basically, you divide the molar mass, okay? But we do multiply and dash line thing, okay? Now, similarly, if you have mole, you can multiply the molar mass or the molecular weight to find the mass of this chemical. At the same time, mole can be also converted into the number of units. Now, this unit could be atoms if you're dealing with elements, or could be molecules if you're dealing with the compounds. The converting factor here is Avogadro number. Every 1 mole is this many molecules or atoms. Similarly, if you have a number of molecules or atoms, you can convert them into moles divided by the Avogadro number. Okay. Now, by looking at this flow chart, you can see if you're dealing with anything convert into or from the mole, it's going to be just one step, like from number of things to mole back and forth, or between the mass and the mole back and forth. Now, if you're dealing with something like, if you're converting the number of atoms to grams, you have to go through the mole as an intermediate, which will take you 2 steps to get to your final desired unit, or the other way around. So keep this in your mind, or have it somewhere next handy. Will be helpful to guide yourself through some of the problems. Okay, so let's take a look at next few examples. Now, if you have 0.451 mole of potassium bromide, and you are being asked for how many grams of it. First of all, you know this is a compound. In order to go from mole to grams, we need the molecular weight. Sometimes we simplify molecular weight to be MW. Okay. Now, if we need to calculate molecular weight, we'll have to be able to write out the formula of potassium bromide. Potassium is K, bromide is Br. The charge is the key because you know this is metal, non-metal. So you're looking at metal, potassium is positive 1 charge, bromide is negative 1 charge. So the compound is going to be just Kbr. Now, given this formula, okay, the molecular weight of Kbr is going to be just potassium plus 1 potassium plus 1 bromine. Potassium is 39.10 plus 79.90. 39 is the potassium, 79 is the bromine. You will have 119.00 gram per 1 mole. So this is the molecular weight of potassium bromide. Now you're starting from 0.451 mole. Kbr. You're trying to multiply 1 step, okay? We know that this is going from mole to grams. So at the end, we have 1 gram of potassium bromide. Now, we're going to stick to the same principle as we have learned from previous section or even earlier in the unit conversion. We're trying to get rid of the mole of Kbr, potassium bromide. We're trying to have the gram, which is the mass unit of Kbr, on top. So you can see this is the molecular weight, the whole thing. This whole thing is the molecular weight. Now, every 1 mole weighs 119.0 grams. So basically, you are multiply the mole by the molecular weight number. Okay. Now, the only thing you got to keep in mind is for any molecular weight, okay, any molecular weight, they are the same as any molar mass of the elements, meaning they are exact numbers. You don't count sig figs of any molecular weight. You only count sig figs of the first number, which has 3. So you keep 3. You just multiply these 2 numbers, okay, and then round down to 3 sig figs. That's it. All right. So let's take a look at another example. Now, if you have 9.4 mole of this compound, which has a formula of CH4, and similarly looking for how many grams of CH4. Now again, 4. Feel free to pause here, try it yourself. Alright, so this is obviously very, very similar to the question we just did, okay? Going from mole, looking at this flowchart, going from mole to grams, okay? This flowchart also works for elements, okay, not just compound. So this is going to be just one step, right? 9.4 mole CH4, one step, and you will get grams. The rule is, I will always write out units and the chemical formula so I know what exactly I'm dealing with. So the desired units will be on top, and what you don't want or you want cancel is going to be only unit, okay, will be here. So every 1 mole weighs how many grams? This will require molecular weight. Molecular weight of CH4. The good thing is you're given the formula, so you can adopt the molar mass of carbon plus hydrogen, and there are 4 hydrogens. So make sure you include the factors if there's any. 16.05 grams per mole. So this means every 1 mole weighs 16.05. This is the molecular weight. Now the same thing, 9.4 times 16.05. You're only counting 6 figures of the first number, which is 2. 150 grams. Okay. All right, next question. If we have 2.54 times 10 to 15 molecule of NO2, and we're looking for how many grams of NO2. Now again, feel free to pause here, try this one, okay? Now the NO2 here though, is not nitrite, okay? Don't confuse between, for example, NO2 versus NO2 minus, okay? This guy is a gas, this guy is an ion. This guy is called the nitrogen dioxide, just like CO2, okay? Think about the carbon dioxide. This guy is a polyatomic ion, it's called nitrite. These are completely different things, okay? All right, so this is a question, if you look at the flow chart, okay, is going from down here, from number of molecules all the way to grams. So you can see you have to go from number of molecules to how many mole first, and then go from mole to grams. It will take 2 steps. Okay, so the way you set up this, started from the number you're given, 2.54 times 10 to 15 molecule of, so we can skip this, okay, NO2, times 2 steps, that means 2 dash lines. And at the end, you're going to get a gram of NO2. So first thing you're going to try to get is, according to this flow chart, you have to go through the mole as intermediate, so mole of NO2 on top. It's very important to specify you're dealing with this compound only, okay? Now the molecule of NO2 down here is going to be cancelled if you're going to put a 1 down at the bottom. Now this is going to be the definition of Avogadro number. So let's review the Avogadro number, okay? 1 mole of anything is 6.022 times 10 to the 23. Now I have 1 mole of NO2 molecule. That's going to be, oh, I'm sorry, 1 mole of NO2 chemical substance. Okay, that's going to equal to 6.022 times 10 to the 23rd NO2 molecule. Okay, so this is going to be rewritten as 1 mole 6.022 times 10 to the 23rd molecule. If you're putting this whole thing into your calculator, be very, very careful, okay? As a matter of fact, I want you to put parentheses in front of any number with exponents. Okay, any number with exponents, especially when you have a scientific notations, okay? So you know so you're certain that the calculator recognizes this is the this is on the top, this is the divider, okay? This is the denominator. The whole thing, 6.022. Alright, so this first step basically converting this number of molecules of nitrogen dioxide into the mole of nitrogen dioxide. And next step is going to convert mole into the mass or the grams of nitrogen dioxide by get rid of the mole. Okay, and this is going to be molecular weight. You have to think about it. 1 mole of NO2 weighs how many grams? So the molecular weight of NO2 is going to be nitrogen 14.01 plus oxygen 16.00, but be aware there are 2 oxygens. So that's going to give you a molecular weight of 46.01 grams per mole. So this number, okay, this number will be rewritten into this, everything in this box. Every 1 mole weighs 46.01 grams. Okay, so the molecules divided by Avogadro number multiplied by molecular weight. Basically, you can ignore the 1, so okay, mathematically. We should have a fairly small number, but keep in mind, you're not counting sig figs of Avogadro number or the molecular weight. The only number you need to count sig figs is the number in the front, which has, let me highlight this, okay, 3. So if you still have a question about counting the number of sig figs, you can go back to module 3 to review that part, okay? And also keep in mind, we're most of the time we're counting sig figs is because most of the time we're doing multiplication or division. Okay, keep in mind that when doing addition subtraction, you're counting the decimal place. So the answer to this question is going to be 1.94 times 10 to negative 7 grams of this guy. All right. So let's take a look at one more example, then we can finish up this kind of calculations. Okay. If we have 80, hold on. Excuse me, 8.97 times 10 to negative 22 grams of water, H2O, asking you how many molecules of water are in this sample. This is going from grams to molecules. You can see this is doesn't seem like you're going to mole or going out from mole. So that's almost certain that you have to go through a mole as intermediate. Let's take a look at this flow chart. Okay. The question was asking you if you have certain number of grams, can you find out certain number of molecules? So in this flow chart, it's basically from mass to number of molecules. So you have to go through the 2 steps. Okay. All right. So have this in your mind, strategy in your mind. Okay. You can start setting up work by, putting down the first number. And make sure you involve the units and the chemical formula. Understanding that there are going to be 2 steps. At the end, you're looking for a molecule. It'll be so much easier if you can set a framework like this and then fill in the blanks, okay? And the first target, which is going to be on the unit of first dash line, is going to be mole. Always look for mole first. And the first unit you're trying to cancel is the gram of H2O down here. Okay, you can even go to the next one, setting up units without filling numbers yet. So the mole of H2O should be cancelled in the second step, and at the end you should be looking for molecule H2O. All right, let's see what number we need here. All right, mole grams. So 1 mole H2O weighs how many grams? Molecular weight H2O, which equals to 1.01. That's from hydrogen times 2, because with 2 hydrogens, plus 16.00, which is from oxygen, equals to 18.02. See, this is the molecular weight of H2O. Okay, 18.02. So that means every 1 mole weighs 18.02 grams. Okay. The second one, every 1 mole H2O is how many molecules? Is this many molecules. This is a fixed number, okay? I've got your number. So you're gonna, the relationship here is gonna be 1 mole 6.022 times 10 to the 23rd. So you should never, okay, you should never abbreviate the molecule to mole, okay? So these are two different things. Okay, you should always spell out the molecule so that you yourself are not gonna be confused. Okay, a mole is a much bigger unit than the molecule. All right, so basic calculation will be this number divide by 18.02 and multiply by the Avogadro number. Okay, again, you only need to count 6 figures of the first number, which has 3. Okay, at the end you're gonna have a fairly good, easy number, 30 molecules of water. Alright, so this concludes the calculation of mass, molecules, and atoms of elements and compounds, okay? I think the most important thing for this part, including the previous video, okay, previous 2 or 3 videos, is this flowchart, okay?